Hi again, everybody. This is MTED110, and today we're going to start Chapter 7. This is Lecture 7A, and this time we're going to talk about how to compute with fractions. So this is a fun section because if you've ever had trouble with adding or subtracting fractions or multiplying or dividing, or if it just seemed very foreign and alien to you, hopefully this chapter will change your mind about fractions. Let me go ahead and pull up the slides and we'll begin. Okay, Chapter 7, Computing with Fractions. So this is from the book. Why do you need a common denominator to add or subtract fractions, but not when multiplying or dividing fractions? Why do you invert and multiply the bottom fraction when you're dividing two fractions? So if mathematics is to make sense, questions like these must be answered, and our students are going to ask these questions because they're very straightforward, very valid questions, and we should be able to provide them with meaningful answers that build off of their mathematical maturity at that level, right? So here's a little bit of a perspective. On the NAEP exam, which is sometimes called the nation's report card, students were asked to estimate 12/13 plus 7/8 on a multiple choice question, and only 24% of 13-year-old students said the answer was close to 2. So just ponder that for a second there. Only a quarter of 13-year-olds, that is students that are about to enter high school, only a quarter of them were able to say correctly that that sum is going to be close to 2. Some popular answers included 1 or 19 or 21. But let's ponder that for a minute. Go ahead and take a moment and see if you can figure out why students might think that the answer is close to 1 or 19 or 21. Think about it for a moment. Hmm. Okay. And then actually, I should say this. You should speak out loud about it, right? So speak out loud for a moment about what you just thought about, and that way it'll help reinforce what you're thinking in your head. Okay, so let's talk about it. There's lots of different reasons. There's no correct answer. But realistically, if you look at it, you're going to see that if you play around with the numerals in interesting ways, then you could get that. One thing you might notice is if you just happen to add the numerators, if you add the numerators and then add the denominators, you're going to get 19 over 21, right? So maybe that's why they said 19, or maybe that's why they said 21. Um, what about one? Where do you think they could have gotten the number one from? Well, with fractions, students often are desperately reliant on algorithms because they're not thinking about the size of the numbers they're looking at. So if you pull this out, this is going to be incorrect. In fact, I should write this in red. This is wrong. Do not do this. If you imagine them doing something like this, right? Oh, maybe we're supposed to cross multiply, right? That's what we're supposed to do. That's not cross multiplying, by the way. We'll talk about that later. And then if they do that, but it's not really cross multiplying, it's like cross adding. And then what they'll get is they'll get 20 over 20, which is 1. So that's another thing. If they're using that algorithm and they don't remember it correctly, and they remember in the wrong algorithm, they might think that that's how you're supposed to work with it. But the thing is that you would never make that mistake if you were actually thinking about these things as numbers and not just numerals, right? Remember in the last lecture, I was saying how if students aren't comfortable with those fractions as representing a single quantity, then oftentimes they'll operate on the numerators and the denominators separately. This is an example of that, or this is a reflection of that occurring. The other thing is this, and this is something that Dr. Chesler and I have talked about before. A lot of students, when they see fractions like, when they see fractions that are smaller than 1 and they add them together, they think that it's always going to be close to 1. And as Dr. Chesler likes to put it, it's because, quote unquote, every fraction is equal to a half. And what happens is at an early age, students get the misinterpretation that fractions are always very small quantities, right? And then if you were to add two small quantities, then you're not going to be bigger than 1. So sometimes that's referred to as the phenomenon that every fraction is equal to a half. And you'll see that, actually. You'll see that in your students. The only way to get away from that type of interpretation is to make sure that your students can make sense of what these symbols are representing. They're representing quantities on a number line, part of a block, all that stuff that we talked about previously. Okay, so here's another one. I want you to pause for just a minute and think about this. Which of these two calculations is easier? Think about it. Yeah, it's an interesting phenomenon, right? Because I'm guessing most of you actually said that this calculation was easier, which is funny because those fractions are a lot more gnarly than these ones over here, right? These fractions over here are pretty simple, basic fractions that you can model with pattern blocks very simply, right? Or Cuisenaire rods, which we'll see in the next lecture. But this one over here, even though the fractions look gnarlier, the calculation is much easier. And why is that? Well, it's because the denominators are all the same. And that's going to be a driving force for the next several chapters, actually. That denominator being essentially a guide for us, and then also helping us figure out how we can do these operations appropriately. We're always going to focus on that denominator because the denominator tells us how many pieces the whole is cut into, right? Remember that from the previous lecture? It's how many pieces the whole is cut into. Okay, so let's talk again about pattern blocks. And I actually got my iPad set up correctly so I can show you that other app that I use. We had previously used pattern blocks to model fractional quantities. And because we can model those quantities, that means that we can use those blocks to model all of the operations. Yeah, you got to ponder that and think about that for a minute. Those models, the pattern blocks and things, we're just modeling quantities with those. But operating on quantities is the fundamental operations, right? Addition, subtraction, multiplication, and division. Remember, what are they, right? Addition is bringing together, subtraction is taking apart, multiplication is repeated addition, and division is repeated subtraction, right? So we have the ability to actually operate and model these operations through these manipulatives, which is really cool. We don't have them physically here in front of us unless you might have some at home, but we can always use virtual manipulatives. All right, so what I'm going to do here is I'm going to use pattern blocks to model these operations right here. Let me go ahead and get some things pulled up really quick, and then I'll switch. Let me just move this up here. I want to keep a list of the problems that I'm doing. Okay, all right here, and then let me go to this. Give me 1 second here. All right, pattern blocks. Okay, so here's this app, pattern blocks, right here. There we go, that's it. And this is what it looks like, and this is actually what I had left on here last time. Let me go ahead and erase this. I'm just gonna clear everything. Clear. Oh, you gotta put this eraser back. No, not now. I'm not going to answer that right now. So this manipulative is all right, or this virtual emulator is all right, but it's there are some non-intuitive things about it. But let's start. So first we want to model 1/3 plus 1/2. That's the problem we're trying to model. Let me just list that up here. This is what we're trying to model. I have no idea what that is. I'm not going to mess with it yet, but what I need to do is look at these denominators. So the denominator here is 3, and the denominator here is 2. So whichever block I'm going to use to represent the whole or the unit, I need to be able to cut it up into 3 equal sized pieces and 2 equal sized pieces at the same time. So that's where a common denominator comes in because I need to be able to model 1/3 and 1/2. And if I want to add those things together, I need the pieces to be the same size. So there's lots of ways to find this common denominator, and we're going to talk about it in just a minute, actually. But you can probably guess, right? You're basically looking for a least common denominator or a common denominator. And in this case, it's 6. So the common denominator of 3 and 2 is 6. And what we're going to do here is we're going to pick a block that lets us model that we can split into 6 equal sized pieces. And there's a natural choice for that. It's the yellow hexagon, right? Thirds are easy to see because this rhombus represents a third. Oops, forgot to do that. Let me erase this. There we go. Put that back. There we go. So this particular emulator, it lets you pull things out, and then if you click on it, it gives you some nicer options. This is one of the things I like about it actually because you can rotate by standard measurements. So now I can put this up here. There's also a grid that it lets you snap to. You can turn the grid on or off. That's up to you. I forget where it is. I think it's, oh yeah, it's down here. So if I click this little circle with a slash through it, that turns the grid off. But I like the grid right now. Okay, so just to emphasize, these things right here, come on, there we go. there, those rhombuses represent a third of that whole, that unit, okay? And then the trapezoids are going to represent halves. Oops, let me move some things. The trapezoids are going to represent a half, right? And that makes sense too. There we go, because boom, I can fit two of them. So the first thing I'm going to do is I have to decide on my unit, okay? And then what I'm going to do is I'm going to actually sketch, quote unquote, sketch the quantity 1/2. And I'm going to do it like this, okay? And then I'm going to sketch the quantity 1/3. Actually, you know what I'm going to do? I need to move this over a bit. There you go, that'll work. And then I'm going to sketch the quantity 1/3. And I'm putting 1/2 on that side instead, or on that side instead, because it's 1/3 plus 1/2, and I just want to be, consistent with the question. And so I'm going to put that there, and I need 1/3. Here's 1/3. Let me erase these things. There we go. Oh, drag those to the trash. Okay, and then now what I'm going to do is I'm just going to label what each one of those things are representing. I'm going to say 1/3 plus 1/2. And then we're going to do exactly what we did before, where we're going to have these circles and they're going to come together. That's exactly what we're going to do, okay? Except in here, what we're going to get is we're going to get this. We're going to get our 1/2. Oops. There we go. We're going to get our 1/2. And we're going to get our 1/3. And I'm just going to rotate this one, actually. There we go. Okay, and then I'm even going to label them here, too. 1/2. 1/3, but then I need an intermediate, not an intermediate step, I need another step, right? Because we haven't actually shown the result. So what we got to do now is we have to do another picture that shows that this is actually going to be 5/6, as it turns out, right? How do I know it's 5/6? I can tell by the picture now, but don't take my word for it. There's that, and then I'm going to put 5 of these sixths in there. So each one of these represents a sixth, remember? Oops, I keep doing that. There we go. Each one of these represents a sixth, and we've got 5 of them. And notice here that I'm making sure that the yellow space agrees in this case, just so that it's even more visually communicative. And then the last thing I'm going to do here is actually label these and say, oh, this is 1/6, 1/6, 1/6, 1/6, and so on. And so I know that the answer is going to be 5/6. Oop, gross. Let's try that again. In fact, maybe I'll give myself a larger circle. Here we go. 5/6. There we go. Suppose I could write 1/6 there too. There we go. So this is how you would model addition. Notice that it's just an extension of what we saw way back in chapter 3. We're just using a different manipulative to model these quantities because this manipulative is better at modeling things like fractions, right? And that's pretty much it. Like, I mean, remember this? This was the same thing we saw. We had both quantities right here and right here because we're adding, so we're starting with two quantities and bringing them together. We had the result right here. But then the last thing we have to do is we have to actually answer the question. We have to convert that into the answer that we're looking for, 5/6. So that's how you would do it. That's how you would model addition, 1/3 plus 1/2 using pattern blocks. Okay, let's do another example. Let me clear all this. So the next one we're going to do is we're going to do, I'll skip a couple of these. Let's do 2/3 minus a half. Let's do a subtraction problem, okay? So we're going to do 2/3 minus 1/2. This is the problem we're trying to model. And just like before, I'm going to try to, oh, actually, I shouldn't say just like before. Remember with subtraction, you start with a quantity and remove something from it. That's what we're going to do right now. So I'm going to start with the quantity 2/3. I just have to actually model it. So I have to pick a unit. In this case, I'm going to pick the unit to be the hexagon again, because I like to if I can. And I'm going to model 2/3. It's not too bad. Here's 2/3. Let me flip this guy. Oop, keep doing that. You have to be off of the pen tool for, otherwise when you click again, it starts writing. What's also weird is you have to put the eraser back. So like if I'm using it here, I have to actually like click down here to put it back. Anyway, there we go. Okay, so this is 2/3, and I'm just gonna write 1/3, 1/3. And then we're trying to take away a half, right? So the thing is, we don't have a half to take away. And we have to use the same idea that we did before. If we're going to talk about halves and thirds, then we need to talk about sixths. So those denominators are our guide once again. So what I'm going to do here is I'm actually going to draw another one of these, kind of like a conversion, where I convert this into sixths. So I'm going to have another one of these. Oh, let me put the pen down this time. Okay, snap right there. And I'm going to convert this into sixths. Right, there we go. And then I'm going to say, oh, this is 1/6, 1/6, 1/6, 1/6. There you go. And 2/3 is 4/6, right? So that works. And then I'm going to go ahead and circle that. And then the next thing I'm going to do is I'm going to circle, or I'm going to like select, you could say, 1/2. I'm going to select 1/2. And again, it's 1/2 of what? It's 1/2 of the unit. So 1/2 is actually right here. And I'm just going to say minus 1/2. There we go. That is 1/2. And then what's the final result? I'm just going to put another arrow down here, or maybe I've got room over here. I do. The final result looks like this. Oh, put that down. Put that over there. We're left with this, 1/6. 1/6, circle. And so that's the answer. The answer is 1/6. And if you wanted to, you could even write it up here. At this point, it's all about how you want to communicate exactly what's going on. But that's pretty much it. That's how you would model subtraction. And all the other problems are really just an extension of that. Yeah, it's very straightforward. And again, it's pretty flexible. There's just a few, there's just a few standards that you want to stick to, namely this type of thing where subtraction is always removing, uh, and making sure that you're labeling things appropriately so that when we look at the picture, we can understand exactly what we're looking at. In fact, you know what? I would even do this to make this clearer. I would say this is 2/3. And maybe I'll even write 2/3 over here, or maybe I'll write it as 4/6, because 2/3 is equal to 4/6, right? And there's other little notes you can put in here. You could say, oh, 1/2 is equal to 3/6, and that's why we end up with 1/6, and so on and so on. Because algebraically, what's going on, right? Algebraically, we would do this. We would find the common denominator. We'd say 4/6 minus 3/6. There's also no undo button on this manipulative emulator, so I don't like that, the fact that there's no undo button. It'd be nice to just go like click, click, click if you made a mistake, or a couple mistakes like I do. Um, okay, so there's that, and we get 1/6. So this is algebraically or arithmetically what's going on. But again, students have trouble with that, and they struggle with that if they don't have the model first. That's what we have to do first, and then we lead them to this so they can make that transition as smoothly as possible. Okay. Anyway, yeah, so that's this emulator. Like I said, if you like it, you can find it on the App Store. It's just called Pattern Blocks, and I think it's like $4, but you do not need to buy it, so please don't if you don't want to. Um, and there are free versions of things like this anyway, so you don't really have to. And if you've got the physical manipulatives, then you've got them there too. You know, you can take pictures of it and put those on your PDF if you wanted. If you've got them at home, you can do that. Okay, so let's get back to the slides really quick and see what we're doing next. Oh yeah, now we're going to talk about some algorithms. So give me 1 second here. Let's pull this up. There we go. Okay, and actually what you should do, try this on your own. I'm going to put the thinker up for just a second here. Uh, uh, yeah, try to do the other ones that we haven't done. So I didn't do these two, and I didn't do these two. So there's four for you to try on your own if you're playing along at home, which you should. So go ahead and think about how you would model those for a moment, and then try writing some stuff down. You can draw pictures too if you would like. All right, now just take some time to write some of that stuff down, draw some pictures, and just see if it makes sense to you. If it doesn't make sense to you, ask about it in the collaboration meeting and we'll go over it. All right, now let's move on. Okay, so we're going to learn about some algorithms here. And this is actually what I had already said a moment ago. In order to add or subtract two fractions, you first need to find a common denominator. And I'm emphasizing that it's a common denominator first, and you'll see why. A common denominator. To find a common denominator, all you need to do is multiply all the denominators together. So even if you're adding like 100 fractions, right? If you want to find a common denominator, multiply all the denominators together, and then what you'll end up with is you'll end up with a multiple of all of those numbers. And so that means that that new denominator that you found is divisible by all the other ones. So that's the idea, okay? That's why and you only need a common denominator. So yeah, there you go. So the result is a number that is a multiple of all three, or any numbers, I suppose I should have written there. And that means it can be divided by all three, and that allows us to make the pieces equal size. So that's the goal, making the pieces equal sized. There we go. So we've got an example coming up here. Multiplying by an appropriate factor of 1 makes the resulting equivalent fractions able to be added or subtracted. So let's look at an example. Let's look at that one from the beginning, actually. 3/8 plus 1/6 plus 1/3. Now, a common denominator is the product of all three, 8 times 6 times 3, which is 144. So what we need to do next is we need to multiply each of these terms by some clever value of 1 that'll make the denominator what we need it to be. And what I had said on the previous slide is that you basically multiply each fraction by the factors that it's missing, the factors that the denominator is missing. So let me emphasize that right here. So in order to get 8 to be 144, you have to multiply by 18. So it's just missing these two factors, 6 and 3. So we're going to multiply by 18 over 18, which is 1. So we haven't changed anything. That's the important part. This is an equivalent expression. We haven't changed anything. We haven't even added anything. We haven't done anything illegal or anything like that. All right. So then the next thing for 1/6. So now we're looking at 1/6, and that denominator is missing factors of 8 and 3. Remember, I said a common denominator. So we need to multiply by 8 times 3, which is 24, and that's where this comes from. And then lastly, the very last one is 1/3, and it's missing the factors 8 and 6. And so we have to multiply by 48 over 48, which is right there. Okay, and then when you do all that math, you're going to get 54 plus 24 plus 48, and then you can write them all over that single denominator because now all the pieces are the same size. That's the key. The thing that lets you go from this step to this step is the fact that all the pieces are the same size. So now we can just count. We can literally count, and that's kind of what we're doing with this addition process. We're saying here's 54 of those things, add up another 24 of those things, and then add up another 48 of those things. What are those things? They're called 144ths. And when we do all that, we end up with 126 144ths. And we're done. We're done right there. That's totally acceptable. And that's the answer. That is the answer. It's 126 44ths. Yeah, but now some of you are probably cringing the whole time or wondering why I'm doing it this way. Well, we're going to talk about that right now. You can see that using this method is a bit inefficient because we're carrying around a lot of extra factors, right? We're carrying around extra factors. Look down here, or just look at this fraction. We can reduce that fraction. I can see a bunch of things that we can reduce right away. Divided by 2 for one, because the numerator and the denominator are both even. So I could factor out a 2 and cancel those 2's, and I would have a more reduced fraction, right? That 2 is like an extra bit of baggage that we're carrying around with us, right? But the idea is this. We just need students first to be able to understand that they need a common denominator. Any common denominator will work. And that's what we start with. We don't talk about least common denominators yet. We're going to talk about those in one slide. There it is. There it is. So instead of just finding a common denominator, it's much more efficient if you can find the least common denominator. And the least common denominator is just the least common multiple of the denominators, the LCM of the denominators. Ah! And that's what we talked about in chapter 11, right? So if you're comfortable with finding least common multiples, then you're comfortable with finding least common denominators. And if you can find least common denominators, then you can add and subtract with fractions. Boom, that's it. All right. So the least common multiple of 8, 6, and 3 is 24. That's the smallest number that's divisible by all three, 8, 6, and 3, right? 24 is divisible by 8, it's divisible by 6, and it's divisible by 3. So if we make the pieces that size, then we'll be able to, it'll be divisible by all three of those numbers, 8, 6, and 3. So let's do that. It's the same process as before, except now the clever ones that we're multiplying by don't have extra factors that they don't need. That's what it is. So here, 3/8 times 3, 1/6 times, I'm sorry, 3/8 times 3 over 3, 1/6 times 4 over 4, and 1/3 times 8 over 8. There you go. And now the nice thing is that in the bottom here, it's going to be basically the smallest number that we could possibly choose to make this work. And then now that the pieces are all the same size, put them all together because we're doing addition, and we get 21/24. And that's the answer. And that's equivalent to 126 1/44. So this is actually equal to this, right? And it's equal to a bunch of stuff because you can start shaving away factors, right? So here, 126 is, what is that? 63 times 2. I'll say that. And then down here, this is 144 is 72 times 2. Now we can cancel those 2's, and then we could reduce that again. We can divide by 3 if I'm not mistaken. Yeah, or we could cancel a 3 in the numerator and the denominator. So that's pretty much it. That's pretty much it. So even if a student is stuck here, they can always complete the reduction process afterward. It's more important that they understand they just need these to be the same size. That's the first thing they have to understand. Then we can start saying, oh, why don't you go for the least common denominator instead? That'll make it easier. So that's the second thing, right? Okay. Um, Oh yeah, so this is a good time to look back, and that's one thing that students will also forget to do with fractions. Does this result make sense in the context of our problem? If you look at the size of those numbers, does it seem like we would get a number that's pretty close to pretty close to 1, right? 21/24. That's only 3/24 away from 1. What's that, an eighth, right? 3, was it 3/24? 8 times 3, yeah, so that's 1/8 away. Does that make sense if we take 3/8 and 1/6 and 1/3, that we would be pretty close to 1? What do you think? Actually, here you go. Ponder it for just a second here. Think about it. Does that feel like it would be close to 1? Hopefully it does, because yes, it is close to 1, and our calculations are correct. So this is a good time to stop and do like a numeracy check, because that's the point here, right? You can check to see if this feels right. Okay. All right, so here are the formulas for adding and subtracting two fractions. These are just straight up formulas. Some I have had students call it the fish formulas. The fish formulas because it's kind of like this swoopy thing that you can do to remember the formula, right? So all you're really doing is you're multiplying the denominators, and then you're multiplying the numerator by the missing factor, the numerators by the missing factors, and then adding the results together. So the reason my students call it the fish formula is because they do this little swoopy thing. They say, let's see if I can get it right. Uh, yeah, AD plus BC. There you go. There's the fish, right? Just do that. And if you remember the fish, then you can add any two fractions you want. Come on, like don't rely on the algorithms, make sense of it, right? It's just nice. Like this is what I would tell a computer to do. If I wanted a computer to compute something, I'd say, computer, here's the algorithm. But we're not computers, we're human beings, right? Accept it, accept the humanity, right? The same fish formula works for subtraction. So what is it? Okay, can I remember it? See, I'm too busy trying to remember the algorithm. I'm not even thinking about the numbers anymore. Which way does the tail go? I think it's, oh yeah, okay, it's this way. Yeah, there we go, the fish. There we go. Okay, all right. Maybe I'll remember that. I don't know. Okay, so quick word of warning here. This is absolutely not called cross multiplying. This is not cross multiplying. Don't call it cross multiplying because it'll mess your students up. It's one of those things that I've noticed teachers often mess up because the look of it is similar to cross multiplying. Cross multiplication is something that you do when you have an equation. So that's the thing. Like ignore this side for a minute, right? Just ignore this entirely, and these algorithms were just showing you how to add two fractions. That's not an equation, that's an operation, right? That's taking two quantities and putting them together. That's what that's doing. There's no cross multiplying going on at all. Cross multiplication is when you have something like this. I'll give you an example. How about like 2/3 equals x over 5? and you wanted to solve for x. Incidentally, this is what we're going to do in chapters 8 and 9. 8 and 9? Yeah, in chapters 8 and 9, we'll talk about this. But solving for x, this is where you would cross multiply. And cross multiplication just says that you basically multiply across the equal sign. So you would do 3 times x and 2 times 5. And then your result would be, what is that? 10 equals 3x. Then you could divide both sides by 3. And then you'll be left with 10 thirds equals x. Right. So this process right here, that's what cross multiplication is. And honestly, the truth is cross multiplication is really just kind of a trick. Like it's kind of like a joke of a trick. In fact, all cross multiplication does is let you skip one step. That's what it does. And let me show you. I'll do the same calculation without cross multiplying, except it's going to take 2 steps instead of 1 to get to this result right here. Check it out. Let me delete these. So what I'm going to do here without cross multiplying is I'm going to multiply both sides by 3. Okay. Now 3 over 3 cancels, and what you're left with is 2 equals 3x over 5. Now what I'm going to do is I'm going to multiply both sides by 5. And I'm going to go times 5 times 5. 5 over 5 is 1, so I can cancel those. And then I'm left with 10 equals 3x. And that's the result. So cross multiplication is quite literally just merging these 2 steps into one. That's all it is. It's not some like special fancy thing. So if somebody thinks it's that special, it's really not. It's just a shortcut. Anyway, but the stuff up here, that is not cross multiplication. So don't call that cross multiplication because it's going to mess your students up big time, big time. Trust me. Or don't trust me. Try it out yourself and see what happens. Okay, so let's use the formula to compute this. It's very straightforward. What is it? The fish. So it should be 1 times 8 plus 3 times 4 over 4 times 8. And let's see, that's going to give us, what is that? 8 plus 12 over 32, which is 20 over 32. Done. There we go. 20 over 32. All right. Now let me ask you this. Is there an easier way to do that sum, to do that addition? Is there an easier way? Think about it for a minute. Well, yes, there is actually an easier way. An easier way is to recognize what the quantities are that we're working with and not rely only on the numerals themselves. Look, this is 1/4. Let me change the color here. This is 1/4. 1/4 is the same as 2/8. So really what we're looking at is 2/8 plus 3/8, which is 5/8, and we're done. Yeah, that's it. So we're done. So like we didn't really need this algorithm. So we shouldn't just go to it as a go-to. I mean, maybe if the numbers A, B, C, and D are like super gnarly or super gross, this might help. But in general, we should try to do this addition problem using our numeracy and our number sense, because it could be a lot easier, right? Incidentally, that's the same thing that we had. What did we have? Like 20, what is, oh yeah, there it is, 20, 30 seconds. Sure, multiply the top and the bottom by 4. Watch. Times 4 over 4, and you're going to get 20 over 32. So they're equivalent. Okay. Incidentally, that the thing is that this formula gives you a common denominator, not the least common denominator. That's the thing. Okay. There's also the number line model. And the number line model is just as easy as, actually, do I have an example here? Oh, we'll do that in a second. It's just as easy as it was way back in chapter 3 or whatever. You're adding, so you're just going to add 2 things. But just like before, you need to make sure that the pieces are the same size. So I'm going to do that right here. Let's do a number line first. Okay, just draw this. And then because these numbers are pretty small, and I know they're going to be less than 1, I'm just going to stick to the unit interval. Okay, so I'm trying to compute this, and just like before when we were talking about pattern blocks, I've got fourths and eighths, and so I need a common denominator. I might as well pick the least common denominator, which is 8. So I need to cut this interval up into 8 equal-sized pieces. Let's do it. And let me actually emphasize this right here. Okay, so 8 equal-sized pieces. The nice thing about powers of 2, like 2, 4, 8, 16, 32, is it's really easy to mark them on number lines because you just keep halving everything, right? So we're going to need a half. We're going to need another half, that's a quarter. We're going to need another half, that's 3/4, and then halve each one of these intervals. This is 1/8, 3/8, 5/8, 7/8. Okay, and then what I'm going to do is I'm first going to highlight 1/4, and I'm going to show it right here. And I'm going to label it too. I'm going to say, hey, this is the length 1/4. And then what I'm going to do is I'm going to add 3/8 to that, which I can do because it's actually marked out on my number line. I'm going to change the color here. Maybe I'll use blue. I think that's what I used in my solutions. And then I'm going to add 3/8. Well, here's 1, 2, 3/8. And I'm going to label that too. I'm going to say there's 3/8. And then I'm just going to do this at the very end. I'm going to say 1/4 plus 3/8 equals 5/8. Then maybe I would even circle that. There we go. Notice I have the plus and the equal sign on the numbers, right? On the numbers, not the pictures or anything like that. But that's how you do it. That's how you model it on a number line. Same thing with subtraction. You would basically go back to like chapter 3 and look at how we modeled for whole numbers. It's the same thing. The only difference now is that you have to consider the denominator and you have to have equal sized pieces, all right? Sounding like a broken record again. I do that a lot in this course. Okay, so fractional number sense. This is actually one of my favorite parts of this chapter. We're going to just go with this example. What we want to do is locate and label points for some other numbers on this number line given the scale below. And we have to be precise, okay? It says be precise, and so we're going to do that. And the idea here is that just having these two numbers marked out wherever we want on a number line, we can use it and extrapolate where pretty much any other number is. In fact, we can. Any other number, we can extrapolate, and we can do it precisely. I'll show you how. Watch. Let's explore. If this is 1/4 and this is 3/4, then if I cut it in half, that's going to give me 2/4. So if I cut it in half, this is quite literally the point 1/2, and each one of these is 1/4 in length, right? See, 1/4 plus 1/4 is 2/4, plus 1/4 is 3/4. So there you go. Now, what that tells me is that I know where a half is. And if I know where a half is, and I know where a quarter is, then I know where 0 is. 0 is over here, right? And notice that my marks are exact. This tick mark right here is exactly in the right spot. It's not an estimation. I'm not just going like, oh, 0's over here somewhere, blah, blah, blah. No, it's precise. It's precise because we can actually do that, right? So keep that in mind. Erase that one. Also, because we know how long a quarter is, we know where 1 is. Here's 1 right there. Pretty cool, huh? So there's 1. And the key idea here is that these distances are all the same because those distances represent the length 1/4, which we were able to glean from those 2 points that are given to us. Okay, so now that we know what 1 is, we can mark where 2 is. Let's try it. Let's see. This length right here is length 1. Let me highlight it. That's length 1. So what I need is like another one over here. And we can be pretty precise. Eyeball it. Yeah, that looks about right. Like right there. Boom. There we go. That's pretty precise, right? And now we know where 1.5 is, and we can mark where 3 is, and we can mark where all sorts of things are. Now that we know the distance between 1 and 2, we can start marking thirds even. So let's do that. We just have to cut this interval right here into 3 equal-sized pieces, which we're going to do. Here we go. Pretty good, pretty good. This is 1 1/3. This is 1 2/3. And so on and so on. And we can keep going that way. What if we wanted to mark out eighths or any of that stuff? We can do that now. And all we needed was that. All we needed was those 2 numbers. And with those 2 numbers, we could do all of that. Isn't that cool? I think that's cool. And that's fractional number sense. That's recognizing the size of these numbers and playing around with them. It's a very important skill to have. All right? Okay, so again, if you want me to do that some more, ask in the collaboration meeting and I will be very happy to. It's fun. You should try it on your own too. Make up your own. Hey, what do you know? There it is. Okay, let's take a look at activity 7A and see what awaits. Activities 7A. Okay, Oh, okay, okay. So activity 7A, there's a few things. For one, you're going to use pattern blocks to model the following operations. So you're going to do exactly what I did earlier on in the video. You can use the website. You can use what did I say? You can use Cool Math for Kids, or you can use Toy Theater, or you can use that other app. You can draw them on your own, but I want to discourage you from doing that because the point here is to get experience using a manipulative so that way you know how to use it in the next class and in the future. So I would say try not to sell yourself short on your own education and actually take the time to do it on one of these websites. Yeah. Or if you really do need to draw them, then if you've actually got the physical ones at home, I suppose you could trace them. But I didn't really leave you enough space because they're kind of big. Like I think the hexagon on this page would be like this big, you know. So, well, that's not a hexagon. What am I doing? That's there you go. And you see what I mean? Like that's not a very professional looking thing, especially if we have the actual virtual manipulatives at our disposal. Anyway, so you're going to do that for several problems using pattern blocks to model operations. Hopefully you practiced that already. And then you're just going to use this strip diagram to model one half plus one third. And then you're going to do the same thing down here. Um, this is actually getting you prepared for the next lecture where we talk about Cuisenaire rods, because that's a lecture where you're going to spend more time at home playing around with these manipulatives, these virtual manipulatives. But we'll get there in a minute. And let's see. And then also, yeah, there's also one of these things where I give you two numbers on a line and I say, okay, mark precisely where all of these numbers are. That's the idea. Yeah, yep. All right, I guess that's it. Okay, then I think that's it for the entire lecture. So I think I'm going to go ahead and say thanks a bunch, and I'll see you at lecture 7B, and I'll see you at the collaboration meetings.